Select the major product of the following reaction. All right, so we're going to look at what we have here. So in our starting material, we have a benzene ring, we have a carboxylic acid, and we have an alcohol. And what we are reacting this with is an acid anhydride. So we have an anhydride. So anhydrides are carboxylic acid derivatives. And it's actually a fairly reactive carboxylic acid derivative. So this is it's less reactive than an acid chloride, but more reactive than the rest of your carboxylic acid derivatives, such as esters and amides, because you have a good leaving group. So this is going to undergo a nucleophilic acyl substitution reaction. So what that means is you're going to replace one side of the acid anhydride with a nucleophile. And so small symmetrical anhydrides are what we're typically going to see for this. It's a good idea for it to be symmetrical so that either way, whichever carbonyl you attack, you get the same product. So we can consider one side of that as being the acyl group and the other side as being the leaving group. Right, so we can explain why that is a good leaving group, and that's because it is resonance stabilized. Okay, so you've got that resonance. That makes this a good leaving group. Right, so because it's resonance stabilized, right? Because a good leaving group is going to be a weak base. So it's not as good as a chloride ion, right? The conjugate base of a strong acid, but that resonance makes it a pretty good leaving group. So if it's undergoing a nucleophilic acyl substitution, we've identified the leaving group in the substitution. Then we need to look at what we're reacting it with to decide what is going to be the nucleophile. So a nucleophile has to have lone pairs of electrons, right? Either lone pairs of electrons or reactive pi bonds. And so the benzene ring, not super reactive pi bonds, so I'd really consider the carboxylic acid and the alcohol. And so of those, your alcohol is going to be the stronger nucleophile. So these lone pairs of electrons do have resonance with the benzene ring, but those aren't going to be high contributors to the resonance hybrid because you'd be putting a negative charge onto carbon, and carbon's not very electronegative. Versus here on your carboxylic acid, you do have more resonance. So your alcohol is more nucleophilic than your carboxylic acid. So this is likely to be the nucleophile that is going to replace that anhydride group. So that means that it's going to be the alcohol that is going to attack that carbonyl carbon, form your tetrahedral intermediate. And we're just shortcutting the mechanism here. Eventually those electrons come back down to reform the pi bond and push out the leaving group. So your oxygen is going to end up with this acyl group transferred onto it. And so that is this product here, which is A. And just to add to this, you might recognize this reaction. It's possible you've actually done this before. This starting material is salicylic acid. And the product that we formed is acetyl salicylic acid. Which you might better know as aspirin. Okay, so the way that we went through and solved this, we saw that we had an anhydride, which is the carboxylic acid derivatives. We identified the leaving group, and then we know it's going to undergo a substitution. So the leaving group is what gets substituted, and then we wanted to look at our starting material and determine where was our more nucleophilic site that would do that substitution.